is a stochastic process, Module 5 continuous time Markov chain, lecture 6 queuing networks. In the last 5 lectures, we started with the definition of continuous time Markov chain, then Kolmogorov differential equation, Chapman-Kolmogorov equation, infinitesimal generator matrix in the lecture 1. Lecture 2 we discussed the birth death process. Lecture 3 we have discussed the special case of birth death process, Poisson process. Then the fourth lecture we have discussed the application of a continuous time Markov chain in queuing models. That is the first special Markovian queuing model, that is MM1Q. Then in the fifth lecture we have discussed the simple Markovian queuing models other than MM1Q. Now we are moving into the sixth lecture, that is for the application of continuous time Markov chain in queuing networks. So basically the queuing network is nothing but a network consisting of several interconnecting queues. Either you can say network of queues or queuing network. In today's lecture we are going to cover the queuing network as the application of a continuous time Markov chain. In the last 2 lectures we have discussed the application of a CTMC, in particular birth death process, but now we are moving into the more general setup of CTMC, that is coming in the queuing networks. That means that the underlying stochastic process of a queuing network is a more general continuous time Markov chain, whereas all the simple Markovian queues, the underlying stochastic process is the birth death process. The study of queuing networks is going to be a very vast area. So, we are going to cover here only very simple queuing networks. The first one is a tandem queuing network. Then we are going to discuss the open queuing network, or we can say open Jackson queuing network, and also we are going to discuss the closed Jackson queuing network. Then followed by that we are going to discuss the application of CTMC in performance analysis of wireless network system. If time permits, I will do it in this lecture, or I will go in the next lecture. So, now we are going to discuss the queuing network. Queuing network is nothing but a network consisting of several interconnecting queues. So, we have discussed already the queues in the 4th lecture. I am giving 3 different examples for the queuing network. So, you can say this as the first queue, or we can say the queuing network as the node 1, which consists of a separate one queue where the arrival comes, waiting for the service. After the service is over, then it moves into the second queue, and this is the separate queues in which the arrival wait for the service. After the service is over, that it move into the next queue. Like that it has many queues. So, this is the one simple example of a queuing networks, and this queuing network is called a tandem queuing network, because the output of a first queue is the input for the second queue, and there is no feedback. The output of the second queue is the input for the third queue, and so on. Like that it is a system in which it has some finite number of queues in series. Therefore, this is called a tandem queuing network. Second type, this also consisting of many queues, interconnecting queues, whereas here the output of the first queue split it into some probability the summation of this probability and this probability is 1, and move it into the input for the second queue as well as third queue. If you label this as the node 1, node 2, node 3, node 4, node 5, therefore, this is a 5 nodes queuing network. The output of second queue and the third queue is the input for the third queue, whereas after the service completion of the third queue, with some probability the jobs or customers can move in again, come to the third queue. Therefore, this type of is called queues with feedback. We call it as a queues with feedback. Then the other proportion, it moved into the input for the fifth queue. After the service is completed, it goes away from the system. So, this type of queuing networks in which the arrivals comes from the outside some source and it departure from the system. There is a possibility the customers who finish the service in the fourth queue, it can depart from the system, not moving into the fifth queue also. So, this is the example for the open queuing network. The third type, here also we have 4 queues or 4 nodes, but there is no output. There is no output of queues from the output from the system, as well as there is no input from the outside the domain. That means there is a constant number of customers or jobs will be moving from one node to the other nodes with these probabilities, and these probabilities are called the routing probabilities, in which after the service completed in the second queue, the customers or jobs move into the third queue. With some probability it will move into the fourth queue. Therefore, this probability is called the routing probability of jobs or customers moving from one node to the other nodes with some probability. So, this is called this type is called a closed queuing network. So, even though I have started with some 3 examples, and these 3 examples are related to the different types of queuing networks, but before I move into the types of queuing networks, let me give the characteristics of queuing networks. So, what are all the minimum information is needed or is provided to study the queuing networks? It consists of nodes and interconnected. So, the interconnected are given by the information routing probability matrix. Suppose in this example, if the node 2, after the service is over, the packets or the customers or jobs are moving into the node 3, then the routing probability is a P2 3. So, P is the matrix, routing probability matrix, and second row, third column element, it is corresponding to the routing probability of customers or jobs or packets moving from node 2 to node 3 after the service is completed. If that particular probability is 0, that means that routing probability there is no path from node 2 to node 3. So, we need a routing probability matrix. That matrix order is a number of nodes in the queuing networks, and the entries are the probabilities values. Therefore, it will be either it will be greater than or equal to 0 and lies between 0 to 1. Obviously, this routing probability matrix will be a stochastic matrix. The row sum is 1. All the entities are lies between 0 to 1. Now, what are all the information is needed in the each node or in the each queuing system inside the queuing networks? You have to provide the arrival process, arrival pattern. If it is enter arrival time is a random variable, then what is the distribution of that? Then you have to provide number of servers in each node, whether it is only one server or multi-server or infinite servers. Then what is the time taken for the service, whether it is a deterministic or probabilistic. If it is probabilistic, then what is the distribution of service time? For each node you have to provide. If it is one server, then what is the service time distribution? If it is more than one servers, then whether they are the identical servers or non-identical, and what is the distribution of each server's service time. Next, what is the capacity of the queuing system in each queues? In each, the whole queuing networks, what is the maximum number of jobs or customers are allowed as a waiting space, in the waiting space, whether infinite capacity system or finite capacity system. If it is a finite capacity system, then if the customers are coming from the previous some other node and if the system is full, then it will be blocked. So, therefore, we should consider what is the capacity of the each queues also. What is the scheduling policy? In what policy the customers are getting served in each queue. So, scheduling policy, whether it is a first come first served or a last come first served or a priority based or a random order. So, we should know what is the service, what is the scheduling policy for the each node. So, if you provide these 5 information for each node and the routing probability matrix, as well as what type of customers are coming into the whole queuing networks, whether only one type of customers are moving inside the different queues or more than one type of customers are in the system. Our interest in this course, how the CTMC is used in the, or CTMC is playing a role in a queuing network. Therefore, I am going to discuss a very simple queuing network in which you can able to get the, you can able to map the underlying stochastic process with the CTMC. Therefore, we can get the some of the performance measures through the knowledge of CTMC. Now, I am discussing the type of queuing networks. Even though I have explained the type of queuing networks through these 3 examples, like that you can frame many more queuing networks, but in this course I am going to cover only these 3 types of queuing networks. Therefore, I have given these 3 examples. So, through these 3 examples I am going to classify the queuing networks as the majorly in 2 parts, that is the open queuing network and the closed queuing network. What is the meaning of open queuing networks? The jobs or customers arrive from external sources, routed to other nodes and eventually depart. Therefore, there is a source and there is a sink also. The external source and it has eventually depart from the queuing networks also. Therefore, that type of queuing network is called the open queuing networks. The closed queuing networks has a fixed number of population, some constant capital K number of jobs or customers circulate continuously and never leave. So, that type of queuing network is called the closed queuing network. That means always if you count how many customers in the system means how many customers in each node. If you sum it up, then that total number is going to be always a capital K, that is a population size. Therefore, no one will leave the system and no one depart from the system also. So, it is a constant number of customers always there in the system at the different queues. You can always convert the closed queuing network into the open queuing network by including one source and a sink. You can convert the closed queuing network into open queuing network. So, in general we can classify the queuing networks as the open queuing network and closed queuing network. The tandem queuing network is the special case of open queuing network, in which all the nodes or the queues are interconnected in a series. Let me start with the very simplest tandem queuing networks with two nodes or two queuing system connected in series. We are going to relate the queuing network with the stochastic process and so on. Therefore, let me start with the random variable x of t and y of t. X of t denotes number of jobs or customers in the node 1 at any time t. Node 1 or first queue, both are one and the same. Y t, the another random variable, that denotes the number of jobs in the second queue at time t. Therefore, the together x of t and y of t, you can think of a vector as z of t is equal to x of t to y of t. That vector is a random vector at any time t, and if you collect over the t, then that is going to be a stochastic process. So, this stochastic process, instead of one random variable, it has a two random variables x of t and y of t, therefore, it is a vector. So, that is a stochastic process x of t comma y of t for t greater than or equal to 0, that is a stochastic process. Since x of t and y of t are the number of jobs in the first queue and second queue, and you are observing over the time how many customers in the first node and how many customers in the second node at any time t. Therefore, this is the discrete state continuous time stochastic process. Also, you assume that infinite capacity in both the nodes, both the queues. That means after the service is over in the first node, it will be immediately arrived into the second node, and if no customer in the system at the time, then he will get the service immediately, the service will be started immediately. Otherwise, the customer who comes after completing the service in the first node, he has to wait till his service started. So, I am making one by one assumption, so that the underlying stochastic process is going to be a continuous time Markov chain. That is my objective. So, for that, now I am making an assumption. The first assumption, the inter-arrival time of a customers entering into the first node, that is exponentially distributed with the parameter lambda, or the arrival process into the first queue is a Poisson process with the parameter lambda. So, the population is infinite, the customers or jobs or packets, for example, packets for the telecommunication system or any communication system. So, the customers are entering into the node 1, that process is a Poisson process with the parameter lambda. Now, I am making the assumption for service, I make the assumption for the service time, that is also exponentially distribution with the parameter mu 1 for the first node and mu 2 for the second node. Other than the inter-arrivals are exponential distribution, I made the other assumptions, that is the service time for the first node and the service time for the second node, both are exponentially distributed with the parameters mu 1 and mu 2 respectively. So, ultimately I want this has to behave as a MM1 queue, and this also has to behave as a MM1 queue independently. Therefore, I make all the assumptions the inter-arrival times are independent with the service for the first node. Similarly, this one is the arrival for the second node is independent of the service of the second node, and so on. So, with that assumption, each queue in this queuing network is going to behave as a MM1 queue, and the departure of the first node, that is will be the input for the second node. And here you can use the Buck's theorem. This is a MM1 queue model. Therefore, using the Buck's theorem, you can conclude the departure process is also Poisson process, because the arrival process is a Poisson and the service rate is mu1. Using the Buck's theorem, you can conclude the departure process is also Poisson process with the parameter of the same parameter of arrival process. Therefore, here the arrival process for the node 2 is also Poisson process with the same parameter lambda. It is independent of the service. Not only that, the departure process is independent of the number of customers in the system and so on, and the inter-arrival. Therefore, you will have a two independent MM1 queue using the Buck's theorem. Now, this will separately act as a MM1 queue because the arrival process is a Poisson with the parameter lambda, and already we made the assumptions arrivals are independent with the service. Service is exponentially distributed with the parameter mu2. After the service is over, the customers leave the system. Therefore, this is a separate MM1 queue because we made a infinite capacity in both the queues. Therefore, the two queues tandem queue, the underlying stochastic process x of t comma y of t going to be the continuous time Markov chain, So, now I am going to formulate the CTMC from the two queues tandem queuing network. The transitions due to arrival or departure of jobs in each queue, based on this I can make a state of the system x of t comma y of t, and that is going to be a continuous time Markov chain. This is not going to be a birth death process because you have a two random variable x of t and y of t, and each one independently a MM1 queue. MM1 queue is the underlying stochastic process for the MM1 queue, that is a birth death process, whereas here you have a together x of t comma y of t. Therefore, this is not going to be a birth death process, it will be a general continuous time Markov chain. So, once we identify this as a continuous time Markov chain, because the Markov property is satisfied by the stochastic process x of t comma y of t, I can go for drawing the state transition diagram. It is Markov in nature because the two queues act independently and are themselves a MM1 queuing system which satisfies the Markov property. The first index is for the number of customers in the first node, and second index is for the number of customers in the second node. So, 0, 0 means in both the queues no one in the system. If one arrival comes into the first node, arrival cannot come into the second node, only the arrival come to the first node. The inter-arrival is exponential distribution, therefore, the rate of moving from 0, 0 to 1, 0, that is lambda. Similarly, there is a possibility of one more customer entering into the system when one customer in the first queue. So, it will be a parameter lambda, therefore, the rate will be lambda for the aux moving from 0, 0 to 1, 0, 1, 0 to 2, 0 and so on. Whereas, after one customer already in the first node, there is a possibility the first node, the server in the first node who would have completed the service before the one more arrival into the first node. Therefore, the service is exponential distribution with the parameter mu 1. Therefore, the system goes from 1 0 to 0 1. That means the customer who was under the service, that service is over. Therefore, he moved into the second queue. Now, the first node has a 0 customer and the second node has 1 customer in the system, and his service will start once he enter into the second node. So, this rate will be mu 1. Now, the situation is the situations are either one more arrival, not one more arrival, one arrival to the first node, or the customer who is in the second node, he would have completed his service. So, that service is over, therefore, that rate is mu 2. Then the system goes to 0 0, or it will go to 1 1 with the rate lambda. So, the same way one can discuss for 1 1 also, that means one customer in the first node, one customer in the second node. So, the one possibility is the first customer's service is over, therefore, it will be 0 2 with the rate mu 1, or one more arrival takes place, therefore, it will be 2 1 with the rate lambda, or the second service would have been finished. So, that rate is mu 2, therefore, it is 1 1 to 1 0. So, these are all the possibilities. The system can move from 1 1 to other states 0 2, 1 2 or 1 0, and so on. So, this is the way you can visualize the different transition arcs and the corresponding rates. So, this is a state transition diagram for 2 queues tandem queuing network. Obviously, from this diagram itself you can say that this is not a birth death process. If it is a birth death process, then it has to be a one dimensional and the system has to move forward one step or backward one step, no other moves. So, here you have a two dimensional Markov chain, therefore, this is not a birth death process, it is a continuous time Markov chain. The corresponding stochastic process is a continuous time Markov chain. So, since we land up the underlying stochastic process is a continuous time Markov chain, now we can find out the stationary distribution, that is our interest. So, all pi q is equal to 0 and the summation of pi I is equal to 1. Now, the pi i's are not just 1 pi I, it is a 2 index term. So, by solving this equation, that means you write the balance equation, then use the summation of probability is equal to 1. You need a condition. So, as long as the rho 1 is lambda divided by mu 1, that is less than 1, as well as the rho 2, that is lambda divided by mu 2, that is also less than 1, then the stationary distribution exists. And you can find out the stationary distribution probability as a probability that n1 customer in the first node and n2 customer in the second node, that is nothing but n1 customers in the first node, that probability distribution is 1 minus rho 1 times rho 1 power n1, and the n2 customers in the second node, that is nothing but 1 minus rho 2 times rho 2 power n2. So, this is sort of a product. The probability of n1 customer in the first node and the probability that n2 customer in the second node together, that is same as what is the probability that n1 customers in the first node multiplied by what is the probability that n2 customers in the second node, and this form is called the product form solution. So, for a tandem queuing network, the stationary distributions are of the product form solution, product form. This together probability is a product of individual m1 n MM1 infinity stationary distribution probabilities. Therefore, this is called the product form. So, this exists as long as rho 1 is less than 1 and rho 2 is less than 1. If it is greater or equal to 1, then the system is not stable. Equivalently, the stationary distribution does not exist. Now, I can extend these two queues queuing network into k queues or k nodes. So, there also my interest is to find out the stationary distribution and the probability of n1 customer in the first node, n2 customer in the second node and nk customer in the and so on till nk in the kth node. That joint distribution is same as product of individual distribution of ni customers in ith node. So, this is a product form. Product of I is equal to 1 to k, and this result is nothing but a stationary distribution of MM1 infinity q. So, this exists as long as all the rho i's is less than 1, and since the arrival is lambda, mean arrival rate is lambda, therefore, all the rho i's are lambda divided by the service rates for the corresponding q. So, once we know the number of customers in what is the distribution of a number of customers in the each node for the k node tandem queuing network, you can find out what is the total number of customers in the whole queuing networks. That means, you have to sum it up all the average number of customers in each node. If you sum it up, that will be the total number of customers in the whole queuing network. And since this is each node is going to behave like a MM1 queuing system, therefore, you can use the average number of customers in a MM1 queuing system, that result, that is lambda I divided by mu I minus lambda I, whereas here all the lambda i's are lambda because it is a tandem queue. And if you sum it up, that is going to be the total number of customers in the system. Once you know the total number of customers in the system is the whole queuing network, using Little's formula you can find out the average time spent in the system. Some books they say average response time, average sojourn time. So, all those things are same. So, the average sojourn time using Little's formula you can get it after substituting expected number in the system divided by the arrival rate, because Little's formula is applied to the queuing system in the sense the arrival rate to the system is lambda and the total number of customers in the system. So, that the whole queue, all that series queuing, all the queues, that whole tandem queue, that you treat it as the one system, and it satisfies all the Little's law conditions, that is first come first served, and the arrival rate is lambda, and after the service is over the system the customers leave the system and so on. So, you can apply the Little's formula and get the average time spent in the system for the whole system, not for the individual queues. Now, I am moving into the open queuing network with the feedback. So, I am just giving one simple scenario of 4 nodes queuing network which with the feedback also. So, this is the open queuing network, and here the assumptions are for each node the service time is exponentially distributed with the mean 1 divided by mu I or the parameter mu I. Only one server in each node and infinite capacity, only one server in each node and infinite capacity of the for each node also. The external arrivals external arrival process to the node I, that is a Poisson process with the rate lambda i's. That means, for the node 1 there is external arrival, that is R 1, there is no external arrival to the node 2, whereas there is external arrival for the node 3, that is R 3, that arrival is a Poisson process, and this arrival is also Poisson process with the parameter R 4. And I have not supplied the routing probabilities. I have not supplied the routing probabilities. So, after the service is over in the first node, with some probability it moved into the again node 1, with some probability it goes to node 3 as well as node 4 in this partition, we can multiply this and this, then with some probability it goes away from the system. So, the summation of this plus this and this probability has to be 1. Sometimes we want to draw this arc, outgoing arc. So, there are two possibilities, either this arc probability is 0 or non-zero whenever the summation of other than the going out, if that probability is not equal to 1, that means 1 minus of summation of probability, that is 1 minus of the summation of probability is greater than 0, then that is the probability that the system is after the service is over, the customers who finishes the service in the node 1 leave the system. Whenever the summation of arcs from the node I to all other nodes, if that summation of probability is less than 1, then the 1 minus of that summation of probability, that is the probability in which after the service is over the customers are leave the system. So, that is the way you can make out the probability for this, otherwise we need to supply the routing probability matrix. So, here I am concluding with the open queuing network with the feedback, and the assumptions are infinite capacity in each node and a single server, and external arrival process is a Poisson process with the rate Ri's, whereas the actual or the total arrival rate, that is different from R 1, because the external arrival rate is a Poisson process with the R 1, but there are some customers after finishing the service in the first node, they are again coming back. Therefore, the total or actual arrival stream into the node 1, that is different from R 1. So, that we are going to calculate later. So, I am going for the routing probability with the notation P of I comma j. P I comma j denotes the probability that the job leaving Q I goes to the Q j. Whenever this probability is a summation of probability that row sum is less than 1, then the probability of a job leaving the system after the Q I, that is going to be 1 minus of summation j is equal to 1 to k. We have k is the total number of queues in the open queuing network with the feedback, and the Pij is the routing probability of jobs going from the node I to node j, either you can say node or queue. The actual or the total arrival rate, that lambda I denotes the arrival rate of a job to the Q I, that can be computed using this formula. So, the lambda I is equal to Ri plus what are all the different rates lambda j, and this is the packets are or the jobs are moving from the Q j to Q I. So, if you multiply this routing probability and the arrival rate, that summation plus the external arrival, that rate Ri, that will give the arrival rate of job to the node q, where I is running from 1 to k. Let me give a one simple situation how one can calculate the arrival rate for any q. Suppose you think of the external arrival rate is R1, and after the service is over, with the probability P, the customers who finishes the service in the first node and come back. With the probability 1 minus P, it leaves the first node. Therefore, our interest is to find out what is the arrival rate for the node 1 with the simple only one feedback. So, here suppose I make it R1 is lambda, that is the external arrival rate. So, the arrival rate to the node 1, that is lambda 1, that is same as the external arrival rate, plus what are all the possibilities in which the node 1 is built up. So, that with the probability P. So, this is a P times, suppose lambda 1 is the arrival rate and lambda 1 times P, that is going to be the proportion, the P is the proportion in which it is coming back, and we can use the Burke's theorem. The departure process is the Poisson process. If the arrival rate is lambda 1, then the lambda 1 times P using the Poisson process split, one Poisson process can be split it into, suppose this is the departure process, the departure process is split it into two Poisson process, lambda 1 P and lambda 1 times 1 minus P. So, the lambda 1 times P, that is feeded again into the node 1. Therefore, that will give lambda 1 times P. So, the lambda 1 is equal to lambda plus lambda 1 times P. That is the way. So, here the arrival rate lambda I is equal to R I plus the summation of lambda j P j I, that is the same thing I am applying for the I is equal to 1. So, the lambda 1 is equal to lambda, that is the external arrival rate, plus what are all the ways you have a input arc to the node 1. So, this point the departure process is a Poisson process using the Burke's theorem. Therefore, suppose you make it arrival rate is lambda 1, therefore, the departure process is the Poisson process with the parameter lambda 1, and the Poisson stream is split into 2 with the one Poisson stream with the proportion P and the another Poisson stream with the proportion 1 minus P. Therefore, you have a 2 Poisson stream with the parameters lambda 1 times P and lambda 1 times 1 minus P. These two are the two independent Poisson streams, and this Poisson stream is fed again into the node 1. Therefore, this is the only one input for the node 1. Therefore, you will have a lambda 1 is equal to lambda plus lambda 1 times P. Like that, if you have many k nodes, you have to write the equation for all the k nodes, then you have to solve for lambda i's, then you will get the what is the arrival rate for the node I. So, here I have only one equation. So, I can get lambda 1 is going to be lambda divided by 1 minus P. By solving this equation, lambda 1 is equal to lambda plus lambda 1 times P. Therefore, lambda 1 is going to be lambda divided by 1 minus P. This is known to me, lambda is known to me and P is known to me. Therefore, using these two I can get lambda 1, that is the arrival rate for the node 1. So, this is a very simplest example, but for any open queuing network with the feedback, by framing these equations, k equations, by solving you can get the lambda i's. The product form solution is valid for the stationary distribution, that is what given as a Jackson theorem. So, the Jackson theorem says in steady state the number of customers in different nodes are independent. The number of customers in different nodes are independent. That means, the behavior of the queuing system is consisting of a behavior of many independent nodes. The Qi behaves as if the arrival stream is Poisson. So, not only each node behaves independently, as if it behaves, the arrival is going to be a Poisson for each node. Therefore, this point it is a Poisson, whereas this point is not a Poisson arrival process, but still in steady state the number of customers in this queue, number of customers in this queue and this queue, all the queue size are independent, as well as in steady state the arrival process for the each node behaves as if a Poisson process, but they are not in general Poisson process. So, in steady state, whenever you have a open queuing network with these assumptions, in steady state this behaves as a independent queuing. Therefore, the joint probability of a n1 customer in the first queue, n2 customers in the second queue, similarly and so on till the nk customers in the kth node. Since each nodes behaves independently, so the number of customers in different queues are independent and arrival or Poisson, and already you made assumption it is a infinite capacity each queue as well as only one server in each queue. Therefore, the arrival follows the Poisson, service is exponential, only one server, infinite capacity. That means, even though it is an open queuing network with the feedback, each node behaves as if a MM1 queue in steady state. That is important. That means, as a time dependent, the system may depends on the size of the other number of customers in the other nodes, but in steady state this behaves independently and each one behaves like a MM1 infinity queue. Therefore, you can get the joint distribution of ni customers in ith node, that is the product of ni customers in ith node. If you make a product, that is going to be the joint distribution, because a joint distribution is going to be the product of individual probabilities if each random variables or if each random variable is independent. Therefore, you can use that logic to get the joint probability as the product form solution. And here rho i's are nothing but lambda i's divided by mu i's, and which is has to be less than 1. I forgot, right? Each rho I has to be less than 1, it has to be stable. Each queuing system has to be stable. So, in steady state you have a product form solution where rho i's are lambda I divided by mu I. You have to find out lambda i's by solving this system of k equations. Lambda i's are the unknown, r i's are given, routing probabilities are given. So, using that solve for lambda i's from these k equations. So, once you know the lambda i's, check whether lambda i's divided by mu i's is less than 1, then the stationary distribution exists. Using the Jackson theorem, the joint distribution is the joint distribution, that is the stationary distribution is of the product form solution. Assuming that each queue behaves as the MM1 queue. So, for any general k queues, not tandem queue, open queuing network with the feedback, you can get the average measures also. The way we have calculated for the 2 queues model or the tandem queue model, the same logic can be used for the open queuing networks with the feedback. We are getting average number, then sojourn time in each node, then mean waiting time in each node, by subtracting the average service time for each node. You have k nodes, so therefore, you are getting these measures for each node. Once you know the results for each node, you can find out the total sojourn time by using the Little's formula, because the Little's formula is valid. Oh, here the external arrival rate is lambda. So, that we have to add, suppose here you have to finding out the lambda, and for the open queuing network the lambda you have to compute by adding all the external arrival rates R1 plus R3 plus R4, that is going to be lambda in this example. So, if you add all the external arrival rates to different different nodes, that summation is going to be the total arrival rate to the system, because to apply the Little's formula you think you consider the whole thing as a one system in which R1 plus R2 plus R3 all are independent. Therefore, the summation is going to be the arrival rate for the system. So, the lambda for that example R1 plus R2 plus R1 plus R3 plus R4. Remarks for the open queuing network. The networks behaves as if it were composed of independent MM1 queues in steady state. That is important. I forgot to write that, in steady state. In time dependent, this is not the case, that I have written as a fourth remark. In steady state, these networks behaves as if it is composed of independent MM1 queue. So, the equilibrium queuing length distribution in a Jackson network is of product form. So, this solution is called the product form solution for open queuing network with the feedback that equilibrium queuing length distribution is of product form. This the previous result can be extended to the multi-server model also. In that model we have taken it as a single server infinite capacity. You can think of each queue is a MM-C infinity also instead of MM1 infinity. In steady state, this solution is valid with the MM-C infinity logic, whereas the time dependent queuing length process are not independent. Therefore, the product form solution will not work, and the time dependent scenario is completely different, and with the steady state or the equilibrium queuing length distribution, you cannot discuss the behavior of a time dependent. It is completely independent, completely the time dependent queuing length distributions are not independent for the each queues. Now, I am moving into the closed queuing network. So, here comparing with the open queuing network, here we have a fixed number of population is moving around the queues. No one leaves and no one enter the system also. Therefore, you keep some k customers in the system. In this example, I have 4 nodes, and instead of either you can have a one server or more than one server is also allowed with the infinite capacity queuing system. And you make the assumption the service time is exponential distribution for each queue and all the servers are identical. Here also you can get the product form solution, and the joint distribution of the system size, that is same as the product of rho i's power ni divided by di's of ni for the k nodes. The small k is the k nodes in the system, and the capital K is the total number of population. So, here these AKs are nothing but the normalizing constant, and the rho i's are in terms of alpha I divided by mu I, and alpha you can calculate by solving this equation, where P is the routing probability matrix. You solve alpha times p is equal to alpha and the summation of alpha I is equal to 1. Using that you will get alpha and substitute alpha i's here, therefore, you will get rho i's. Then you substitute dI's here based on the number of servers in the each node is 1 or more than 1, accordingly you can use this. And once you know the dI, ni substitute here, this product form solution will give a joint distribution of a system size in steady state, and this result is given by Jordan and Neville for the closed queuing network. As a remark, this equilibrium solution is also product form, and the routing probability matrix is a stochastic matrix. And suppose you assume P is irreducible, then the solving alpha P is equal to alpha and the summation of alpha is equal to 1, that is nothing but alphas are nothing but the stationary distribution whenever P is irreducible. Not P is irreducible, the underlying DTMC is irreducible, with the assuming that the underlying DTMC is irreducible, then the alpha is nothing but the unique stationary distribution, and this is valid for the cyclic queue also. And the toughness is how to compute A of k, where k is the number of customers in the whole queuing network. So, you need a efficient and stable computational algorithm for calculating this normalizing constant A of k. Here is a mistake, assuming that the DTMC is irreducible, alpha is a unique stationary distribution. So, now we will move into the summary. So, in this lecture we have discussed the applications of CTMC in tandem, open and closed queuing networks. We have discussed the stationary distribution and other performance measures for the tandem, open and closed queuing networks with only the product form solutions. We did not discuss the non-product form solution, we have only discussed the product form solution. And the application of CTMC in the performance analysis of wireless network system, that I will discuss in the next lecture. Also, I am going to discuss the simulation of simple Markovian queuing networks in the next lecture. These are all the reference books. Thanks.